Okay, here's my take 2 on Faraday's Law. I did this all and then realized I was at 15 minutes, stopped it, and of course it was too long to upload to YouTube, so I have to start over. Anyways, let's try this again. I might need to break it into 2. So Faraday's Law, who I want you to know is Faraday is someone that did a lot of work in electrochem, right? He did a lot of work, research, experimentation in here. A lot of the terms that we use are because of him, right? He coined the terms like anode, electrode, cathode. I listed a bunch of terms that he's responsible for. One thing that we specifically use his name associated with is in electrolytic cells, which you guys have just been learning about. If you wanted to figure out how much product could be made at either electrode, you could use it using some of Faraday's work, right? He figured out that the amount of product is directly proportional, as you can see underlined here, is directly proportional to the amount of electricity you're putting into the cell. All right, so that's what we're going to learn to work with, right? Using that relationship to solve some problems. All right, so let's just talk about how we defined a Faraday. We defined 1 Faraday as the amount of charge carried by 1 mole of electrons, right? So 1 mole of electrons. So you have to recognize that each electron carries a charge, right? So a mole of electrons would obviously carry a significant amount of charge, right? Because that's a whole lot of electrons. 6.022 times 10 to the 23. All right? So 1 Faraday, if we have 1 mole of electrons, we could reduce 1 mole of sodium ions, right? Because each sodium ion needs 1 electron to become pure sodium, right? So if we have a mole of electrons, we can reduce a mole of sodium ions. And in pink here, I had written this reduction reaction, right? This half reaction. If we have the same amount of electrons, 1 Faraday, right, we can only reduce a half a mole of magnesium ions, right? That should make sense because the same amount of electrons is going in, but now each ion is taking 2, right? Instead of just taking 1, the relationship's no longer 1 to 1. Each ion is taking 2, and so therefore we can only reduce half as much. All right, each ion takes 2, so we can only reduce half as much, or half as many of the ions. If we have a 3 positive ion like aluminum, right, then we can only reduce a third of the ions that that would have been done if the relationship was 1 to 1, right? So each aluminum ion takes 3 electrons, right? So we can only do a third as many ions because each ion is taking so many more electrons itself. So that's important to know, and that's going to apply to the math that we're doing later. All right, next page, next lesson. So, just to review some electricity terms and units. First of all, and a lot of these, most of you have taken physics have seen, current is the flow of electrons. Its symbol is capital I, and it's measured in amperes. Charge is the measure of a deficiency or excess of electrons, right? A positive charge has lost electrons. Something that's negative has gained electrons. All right, its symbol is capital Q, and it's measured in coulombs, which is capital C. All right, the formula for charge is I times T, right? So the total charge is the amount of current per unit of time, and time is in seconds. The charge of 1 electron is 1.6 times 10 to the negative 19 coulombs. All right, so if we have a mole of electrons, right, 6.022 times 10 to the 23 electrons, how many coulombs is that? So we could do that math, and if I punched it on my calculator, sorry, that's really messy there. I could maybe erase it. Oops, that's not erasing. There we go. 6.022 times 10 to the 23 times 1.6 times 10 to the negative 19. You get something close to this. 96,352 coulombs. What I want you to recognize is that when we're dealing with a mole of electrons, right, Avogadro's number is 6.022 times 10 to the 23. Okay, I have it plugged in. Why is it saying that? It is plugged in, is it not? Why is it not working? Maybe this is okay. It's still not registering. What the heck? What's wrong with my cord? Hold on. think I had my charger in upside down. Anyways, so 6.022 times 10 to the 23, that's a rounded number, right? It would actually be 6.022, blah, 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 lots of numbers after that, right? So we're using an approximation. If you were to take more places and times it by the charge of electron, it actually ends up being closer to 96,500. So that's what we're going to use. 1 Faraday is 96,500 coulombs per mole of electron. Right, so you need to know that number. And the formula that we could use to figure out moles of electron is to take the total charge, if you knew what it was, and divide it by that number, divide it by 96,500. Now I have all of these numbers scribbled on the side. I'm going to erase them and start over. Right, I was just saying earlier when I first tried to make this video that this should make sense, right? What this formula is telling you is, for example, if you had 193,000 coulombs of charge, right? If you divided that by 96,500, it would suggest that you have 2 moles of electrons, right? Because you have twice as much charge, you have twice as many electrons. You could also divide that by 1.6 times 10 to the negative 19, and you end up with something very close to 1.2 times 10 to the negative 20, hold on a second, now I forget the number, 193,000 divided by 1.6, should be 24, right? Yes, 24. I was just nervous for a second, right? So that many individual electrons, well, wait a second, and it's not negative 24, that's why I was having issues with this, it's positive 24, right? So let's just think about this again, right? So if I was to divide 193,000 by the charge of a single electron, 1.6 times 10 to the negative 19, I get this number. Well, that number looks familiar, right? Because it's twice Avogadro's number. It's 2 times 6.022 times 10 to the 23 because we have 2 moles of electrons. Okay, so that's what this formula is telling us. You could take the total charge, whatever it might be, and figure out either how many moles of electrons you have by dividing by 96,500, or how many individual electrons you have by dividing 1.6 times 10 to the negative 19. Okay, and of course we can adapt that formula to IT, because that's what total charge is equal to. I showed you that formula over 96,500. This is on your formula sheet, right? This formula right here, so you'll need to use it. So then I want to do 3 examples. I'll maybe do one on this video, and then before I run out of time, sorry, excuse me, I will do my last one. Now, unfortunately, I guess I could quickly erase this. I have all the answers on here because I have already done it once, but we'll just erase it and pretend like you didn't see it. Okay, so determine how many moles of electrons are supplied by a battery with a current of 0.1 amps for 50 minutes. Okay, so this is just straight using the formula, moles of electrons. The biggest thing is when you're doing IT over 96,500, that you remember that T is in seconds. So we will take 0.100 amps of current and multiply it by 50 by 60. Right, just changing that to seconds. And then dividing by 96,500, and you will get 0.00311 moles of electrons. All right, so I'm going to upload this video and start on the last 2 examples.